Hello, I'm Mr. Bob and welcome to my Algebra 1 video series. This video covers Chapter 5, Section 5, titled Direct Variation. By the end of this video, you will have reviewed processes for writing the equation of a direct variation, and then you will look at ratios, proportions, and direct variations. You will start by reviewing what a direct variation is. You will write an equation given a point, and then you'll handle a real-world problem. While looking at ratios, proportions, and direct variations, you'll look at tables in relation to direct variations and then end with another real-world problem. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find this video helpful. Please, yeah, I would greatly appreciate it. At least subscribe. Leave a like if you can. It'll help the channel be seen by more students like yourself. Thank you. Okay, objective 1, writing the equation of a direct variation. When a film, let's imagine what's going on here. When a film is projected, the number of frames doubles as the number of seconds doubles. So the longer you're running a film, these frames keep flying by at so many frames per second, so to speak, right? So if you run for 2 seconds, you're going to have twice as many frames that have gone through the projector as it went through for 1 second. The number of frames is proportional to the number of seconds. That is, the number of frames varies directly with the number of seconds. And what's this definition of a direct variation? A function in the form y equals kx, right here, y equals kx, where k is not 0, of course k cannot be 0, okay, is a direct variation. The constant of variation, k, is the constant of variation. It's the coefficient of the x variable right there. K is the coefficient of the x variable. The variables y and x are said to vary directly with each other. As x goes up, y goes up. As x goes down, y goes down, right? So for y equal kx, y is a function of x. If x is equal to 0, then y is equal to 0. So the graph of a direct variation is a line that passes through 0. To tell whether an equation represents a direct variation, solve for y. If the equation can be written in the form y equals k times x, it represents a direct variation. Okay, example 1. Is an equation a direct variation? That's what we're going to try to determine here, right? So is each equation a direct variation? There are 2 problems, 2 equations. 5x plus 2y equals 0. So the first thing we're going to do is, like I think I said before, we're going to solve for y. So in order to solve for y, in this case, we're going to move the 5x from the left to the right. And by doing that, we have to subtract 5x from both sides. And you see that right here. We've subtracted 5x from both sides, and we're left with 2y equals negative 5x. Okay, because we subtracted 5x from both sides. So once we do that, now I have to get the y by itself, which means we have to divide by 2 or multiply by the multiplicative inverse of 2 to get the y to stand by itself as y with a coefficient of 1. So when we do that, we're going to get y equals negative, because it started with negative 5x, negative 5 divided by 2 times x. So the equation has the form y is equal to kx. And the k in this case is what? The constant of variation is the negative 5 over 2. How about 5x plus 2y equals 9? Well, same thing. We're going to move the 5x just like we did last time. So we're going to subtract 5x from both sides, and we're going to get 2y is equal to 9 minus 5x. Then we're going to divide both sides by 2 to get rid of the 2 with the y to get the y by itself. So now we have 1y is equal to 9 halves minus 5 halves x, because we've divided both sides by 2. But this equation cannot be written in the form y equals kx. And why is it not? Because what do we have right here? This term right here doesn't allow, if this was 0, if this term didn't exist, then we'd have what we had above. We'd have a direct variation. But this has the 9 halves in here. And so therefore, it is not a direct variation. Not. Okay, example one, check your understanding, right? So that means that I want you to pause the video and try these on your own. And then when you come back, we'll work them together. I'll give you about 5 or 6 seconds to pause and then return. Okay, I'll wait for you. Okay, assuming you've had time to do that and you're back with me. So it says, is each equation a direct variation? They're just asking the question, is it or is it not? And if it is, write what is the constant of variation. So let's look at the first problem. The first one is 7y equals 2x. So in order to determine this, we have to solve for y. That's the first thing you have to do. And then we'll see if it's in the kx form, right? Y equals kx. So solving for this equation, we're going to divide both sides by 7. That's going to get our y by itself. So what are we going to have? We're going to have y is equal to 2/7 x. So the answer to this is yes, this is a direct variation, and the constant of variation is equal to 2/7. Okay, let's go on to the next one. How about b here? It says 3y plus 4x is equal to 8. Okay, again, solving for y, we're going to subtract 4x from both sides. We're going to have 3y is equal to 8 minus 4x. And we're going to divide both sides by 3 because we want to get the y by itself. So we're going to divide by 3 over here and divide the 8 by 3 and divide the 4x by 3, the negative 4x. And we're going to get y is equal to 8/3 minus 4/3 x. So the answer is no, this is not a direct variation because I'll circle it here, because this piece right here, make sure that we're not in the form. And what's the form we're looking for? We're looking for y equals kx. Okay? How about this number c, or letter c? Y is equal to, well, negative 7.5x. And that equals, well, it doesn't say that. I'm going to have to, sorry, I'm ahead of myself in my brain, right? Sorry about that. Please forgive me. Let's get back here. Writing the equation, y minus 7.5x equals 0. We have to get the y by itself, so we're going to subtract or add 7.5x to each side. So y will be equal to, we're going to add 7.5x to this, to the left-hand side. It'll delete this 7.5, and that equals plus 7.5x, right? Because it's 0 on this side. And when you do that, it is a constant. It is a direct variation. And what is the constant? K is equal to 7.5. Okay, good. Okay, example 2, it says writing an equation given a point. So now they're going to give you a point, x comma y, right? Ordered pair. Okay, and then they want us to write the equation that is a direct variation that goes through that point. So what do we start with? We say write an equation of the direct variation that includes the point 4 comma negative 3. So the first thing we do is we write the standard form of the direct variation equation. Y is equal to k times x. And then we're going to substitute for the y. The y in our ordered pair is the negative 3. So we put a negative 3 there. And the x of our ordered pair is the 4. So we substitute a 4 for x. So we get negative 3 equals k times 4. Now we want to find out k. That's what we're trying to do, is get the constant of variation to write the equation. So once you have the constant of variation, it's easy to write that simple equation, because we're going to then substitute that back in for the k up here in the equation. And how do we get that? Well, we'll have to divide both sides by 4, because we have to get the k by itself to know what the constant of variation is. So we divide both sides by 4, we get negative 3 divided by 4 is equal to k. And then now we know what k is, we can substitute back in the function, the direct variation function, the standard form, and we get just what we have written right here. Y is equal to negative 3/4. Here's k is equal to negative 3/4. So y is equal to negative 3/4 times x. Okay, so the equation of the direct variation is y is negative 3/4 times x. How about we're going to check your understanding right now. So let's go ahead, and this is example 2, check your understanding. Write an equation of the direct variation that includes the point -3, -6. Okay, I'll wait for you for a little bit to try this. Okay, assuming you've had time to do that. So let's do it. So what's the standard form of a direct variation? It's y equals kx, right? So what we need to do is find the k value, because then the y and the x values are going to take care of themselves. So how do we find the k? Well, we're going to substitute in our ordered pair for the point we want to go through. Okay, so we want to be able, this line that we're going to create now has to go through this point, -3, -6. So we're going to, the -6 is your y value. Okay, so we're going to say -6 is equal to, and the x value is the -3, is equal to k times -3. Now, in order to find k, we're going to solve for k, and we're going to divide both sides by -3. And when we do that, we're going to get 2 is equal to k. Now that we have k equal to 2, or 2 equal to k, we're going to substitute it back into our formula, our standard form of a direct variation. We're going to say y is equal to 2x. Okay, example 3. It's our real world problem, one of the two that we were talking about. Okay, so this is kind of an interesting little real world example. Your distance from lightning varies directly with the time it takes for you to hear the thunder. So the farther the lightning is away, the longer it's going to take you to hear it. So if you hear thunder 10 seconds after you see lightning, that means it's about 2 miles, that you are about 2 miles from the lightning. 10 seconds means about 2 miles. Okay? So let's, it says write an equation for the relationship between time and distance. So let's first of all try to reword this so that we can convert this into an equation. So the distance varies directly with time. And when time is when x is equal to 10, y is equal to 2. And the distance is the 2. Okay, and the time is in seconds, 10 seconds. Define, it says, let x equal the number of seconds between you seeing the lightning and your hearing the thunder. Okay? Let y equal your distance in miles from the lightning. So now we're going to write an equation here. So we're going to start with the general form of a direct variation. Right, y equals kx. Then we're going to do some substituting. So y is the distance in miles. That's what you're trying to determine. So you're going to see lightning and you're going to start counting seconds. And then whenever you get to, you're going to be able to plunk it into your equation and figure out how many miles it is away. So y is the distance in miles, right? It's 2. And then k times 10. 10 is seconds. So that's what you did. You sat and you listened about, you got the 2 miles and 10 seconds. When you do that, now you have to solve and get that constant. Oh, what is that constant? The constant is divide both sides by 10, and you'll get 1/5 equals k. Because I could have said 2/10 equals 1/5, and that equals k, because you divided each side by 10. And when you do that, you're going to get y. Now your equation is y is equal to 1/5 x. Y is equal to 1/5 x. So the equation y equals 1/5 x relates the time in seconds it takes for you to hear the thunder, the distance in miles you are from the lightning. Okay? Okay, example 3, check your understanding. A recipe for a dozen corn muffins calls for 1 cup of flour. It's a dozen muffins, 1 cup of flour. The number of muffins varies directly. The muffins vary with the amount of flour. So use the direct variation for the relationship between the number of cups of flour and the number of muffins. So it says here the muffins varies directly. The muffins vary with the amount of flour. Okay? So what is that going to tell us? You're going to figure that out. So pause the video, try it, and when you come back, we'll work it together. Okay, I'm assuming you're back. Let's give this a look, okay? So what it's saying is what the muffins are varying with the x value. So muffins are the y value. So in our case, y is equal to kx. The y is 12. 12 muffins, okay, is equal to k times some x value. And what is it? Per cup. So the muffins vary directly. They vary directly with the amount of flour. So now solving for k, we're going to get 12 divided by 1. K is equal to 12. So our answer is y is equal to 12x. That's it. Good job. Okay, objective 2a, ratios, proportions, and direct variations. You can write a direct variation, y equals kx. We've done this a bunch of times now. Y is equal to kx as y divided by x equals k. And we know that because that's how we've been solving for k all along, dividing y by x, and we get k, right? So when 2 sets of data vary directly, 2 sets of data, the ratio y divided by x is a constant of variation. It's the same for each pair, okay? So you'll find out that if we have um, one xy pair is 1 comma 2, and that's one pair, and we have another pair which is 2 comma 4. They're both the k values here, k of 2 here and the k of 2 here, right? So this is the direct variation. This is your constant. These have to be the same if it is a direct variation, right? Okay, so let's look at it. We're going to see some of this. Example 4, direct variations in tables. So now we're going to look at that. So it says for each table, use the ratio of y to x to tell whether y varies directly with x. If it does, write the equation for the direct variation. Okay, so let's take a look at it. We have an x value, we have a y value, right? And we have a y divided by x. So what did this say? If they're the same, if the k values for each set of data is the same, it's a direct variation. So if we look at this first one, if we look at the very first one, we're going to get what? We're going to get y divided by x. So we're going to get 2.25 divided by negative 3, and it gives us negative 0.75. I'm going to change colors. When we go to the next one, we get 0.75 divided by 1 gives us negative 0.75. They're all negative, by the way. If we take negative 3 divided by 4, that's 3/4, right? Negative 3/4, so negative 0.75. And then the last one, 4.5, negative 4.5 divided by 6, 4.5 divided by 6 is equal to negative 75. This is definitely, yes, it's a direct variation, and the constant of variation is the negative 75.75. That is the constant of variation. And what is the equation? The equation is right here. Y is equal to negative 0.75 times x. Let's look at the next one. So they want to know, are these k values, so to speak, are they the same? If they're the same, it's a direct variation. Well, right off the bat, you can see something's different. In this one, the very first term, negative 1 is divided by 2. That's going to give us negative 1/2. The next one is a positive. 1 divided by 4 is a positive quarter. But guess what? This is negative. This one's positive. It already, you know, it cannot be a direct variation because you have a negative and a positive. They're not the same number. Now you have on the next two, you have 0.5 and 0.5. So the 0.5s are here. You got a negative. It still doesn't make any difference. You can't just have two the same. They all have to be the same. This is not a direct variation. Okay, example 4, check your understanding. For the data in each table, tell whether y varies directly with x. If it does, write the equation for the direct variation. So let's look at problem A. Oh, this is yours. So why don't you pause the video, give it a try, try these out, see what you come up with. I'll wait for you. Okay, so here we go. Let's look at A. So we have an x and a y value. So what do we have to do? We have to divide y by x on all three cases and see to make sure that they're all the same. Well, we start off with 3.2 divided by 2. It's 1.6, right? Negative. Then we have 2.4. Well, right off the bat, there's two reasons why this is not. This is negative here, negative and positive. So that's already a failure. And this is 1.6 and this is 2.4. So here's a 1.6 here, but this is negative 1.6. This is positive 1.6. This is not. Oops, I'm going to write it right here. I changed my color. Sorry. This is not. Oh, come on. There you go. This is not a direct variation. Okay. How about this one? 6 divided by 4 is equal to 3 halves. Okay. How about 12 divided by 8 is equal to 3 halves, right? You can take a 4 out of both of these. 12 is a 3. If you take a 4 out, 8's a 2, right? And how about 15? You can take a 5 out of each of these in the bottom and you get what? You get 3 halves. All these constants, these are all constants that are the same. It is definitely, yes, it is a direct variation, YES, and guess what? What is that? It's y is equal to 3 halves x. Okay, objective 2, ratios, proportions, and direct variations. So in a direct variation, the ratio y to x is the same for all of the data pairs, right? The x comma y ordered pairs. The ratio of y to x is constant for a direct variation. So, and x cannot be equal to 0, of course. If it is, it's undefined. However, so the proportion y1 divided by x1 is equal to y2 divided by x2. All right, so let's try one. I would say, how about this one? I'm going to say 1 comma 2, and the next one I'm going to say 2 comma 4. Is this direct? Yes, because this is what? 2, and this is 2. So the k value is 2 for both of these, y divided by x. So that's what we're talking about, okay? So, and x1 and y and x2 cannot be 0. So there you have that. So, and then I've drawn a picture. I've got a picture here and a little definition that you probably would like to know because we're going to use it in the next slide. It's a windlass, maybe a windlass, but it's windlass. Okay, but they are winding, right? Winding lass, like a lasso almost. Anyway, so what is it? Any of various machines, any of various machines for hoisting and hauling. And here's a picture of a windlass. So it's a crank, but there's no gears on it in the sense that there's a gear to keep it from going backwards accidentally, because it's going to have a lot of tension on the cord over here. There'll be a lot of tension over here. And you wind the crank around clockwise in this case. And as you do, you see there's a rope wound around the spool. Well, you might have to wind it around a couple times, but you can use the friction between the rope and the spool and the rope. You can use the friction between them. You see it right here in the middle with the crank to put tension on this line here, and it'll pull up, in this case, this anchor from the bottom, a 100-pound anchor, is being lifted from the bottom of the sea with this crank. And it doesn't wind up anything. There's no winding reel because the rope just keeps coming off and pouring into a big pile on the floor. It's usually the job of someone to wind it as you're cranking that in. Someone will stand there helping you wind that up so it don't get balled into a big knot. Okay? There you have it. Now you know what a windlass is. A windlass. Windlass. That's how it says it's pronounced. Windlass. Okay, example 5. Here's your second real world problem. The force you must apply to lift an object directly varies with the object's weight. Keep thinking about our windlass, right? How we're going to crank the force, the pounds of force it's going to take to crank that crank. Okay. You would need to apply 0.625 pounds of force to the windlass to lift 28-pound weight. That's how much weight based on the gearing, and that's the spool size. Okay, how much force you have to apply, and how big the handle is, force you have to apply to lift 28 pounds. How much force would you need to apply using that same windlass to lift 100 pounds? So we're going to write this question in the form of a sentence or a statement that can help us put this into an equation. It says, so a force of 6.625 pounds can lift 28 pounds. What force lifts 100 pounds? Well, we're going to let N equal the force needed to lift 100 pounds because that's one thing we don't know right here. What force? That's our N value, okay? So write the proportions here we're talking about, right? So what do we get? We get force 1 divided by weight 1 equals force 2 divided by weight 2. Force 1 is 0.625. Weight 1 is 28. Those are the two that they're giving the information on. 625 can lift 28 pounds. So that's a relationship that goes together. And now we want to know the force it takes here to lift 100 pounds. That's the second piece of this. And we're solving for x. In order to do that, we're going to cross multiply. So we're going to get 6.625 times 100. And that's equal to 28. Okay, n. So when you do the math, that ends up being about 2.2 foot-pounds or pounds force, right? So there you have it. So you need about 2.2 pounds of force to lift 100 pounds. When I did make the mistake and said foot-pounds, that would come into being how long the handle is. So here you got the windlass, and you've got a handle. Well, if this was 1 pound to push on the handle, and the handle was 12 inches long, and it took 1 pound of force to move it in this direction, that would be 1 foot-pound. 1 pound, 12 inches is a foot, 1 foot-pound. If it took 2 pounds to crank that crank, it'd be 2 foot-pounds. Or if the handle was longer or shorter, so that's the mathematics on where you get foot-pounds of torque from. Hopefully that's helpful. Okay, example 5, check your understanding. It's your turn. Suppose a second windlass requires 1/2 pound, 0.5 pounds of force to lift an object that weighs 32 pounds. How much force would you need to lift 160 pounds? Well, again, what was that? Oh, I'm not, it's your turn, right? I'm going to let you solve it and then come back. I'll give you some time. Okay, so now let's take a look at this. I've highlighted some of this and wrote out the answer here so you can, we'll see if yours comes out the same. So I have, as before, I have the force of 0.5 pounds. Okay, is our force 1, and our weight 1 is 32 pounds, just like before. And the force you need to lift 160 pounds, right? So we're saying N and 160 pounds. So force 1 divided by weight 1 equals force 2 divided by weight 2. Let's do some substitution. Force 1 is 0.5. Weight 1 is 32. Here's N, and 160 is weight 2. When we do the math, we do the cross multiplication, we get 0.5 times 160, is equal to 32n, and that's so this ends up being 180, right? Is equal to 32n, so 180, not 180, 80 is equal to 32n. So now you want to know how many times does 32 go into 80, and its n will be equal to 2.5 times. So you need 2.5 pounds of force to lift 160 pounds with that windlass.